Okay, we should start. So, what are we going to do today? So first, I would like for you to spend 10 minutes filling in the final evaluation, because that's something that we're all very crappy at filling in. And so let's, yeah. Just a little bit, you have to fill in manually. Yeah. But that's why I'm reserving some time now so that it doesn't impinge on your very busy schedule. Yes. Just another thing that we're reserving time this week. Final evaluation that I was thinking. Ja, men også fordi for jeg ved ikke, om det får det lidt godt med mig, det laver det. In the evaluation?
Was it the base inference as a prompt?
Uh-huh.
That was the prompt. And then I asked, what does it make you feel like? And then I said, I want to die.
But what was the base rate of that person saying I want to die? That's the crucial.
It was an anomaly. It was an outlier. Yeah. Most people did not feel like this is really not. So that's good. Oh yes, it's really difficult to hide, right? If you die, then you face your family something. If you last month's life saving was higher than mine. No, yours was like 50 and mine was. It was yeah. If I die, my parents get 411. Yeah, that's money. That's really rich. No, what do they do? All that position. Du er også klar til alt med det.
Så det gælder ikke. Så var det skudt. Det var 2 åbne spørgsmål.
Det var det ikke. Det var sådan. Let's stay in the let's stay in the like Microsoft's.
Yeah, that's when I get bored, right? And then I just, ooh, let's see which kind of silly So look at this.
Very creative.
Yes. It's also, you can see like year from year, what else is it gonna suggest? Like there was a period where every time I would say model or computational model, there would be like a sexy robot. I think now I only get 2 sexy robots facing each other and zooming in on the face. I don't know if it's an improvement or.
Okay.
So. Are you all done? Good. So we should then start. Thank you. I'll have a look at the final evaluations and then try to do a summary by Monday when we have the last lecture. Okay, so what we're gonna do today is we're gonna zoom out on models of categorization, the stuff that we were skipping last time to make sure there was some time to discuss the GCM. We're gonna discuss the 3 main clusters or 3 main categories of models of categorization. That is exemplars, prototypes, and rules, which also resonate with your intro to CogSci course. We might spend some time to figure out how does this relate to machine learning classification, right? Are we learning something useful? Like, does it even make sense to compare the two? And if so, what can we learn? Then I have the conclusion of the discussion on how to make a stand model, or the discussion of how to make a stand model of the GCM. And finally, usually I leave my last lecture a bit open because there's always stuff to catch up with. Well, I would like to hear whether there are specific things that could be useful to you to see, right? Which could be from live coding of a model to discussing what are the current frontiers of these, to discussing like how would we even implement this in order to make better research in a given area. Wow. So think about that. I might just ask you at the very end of this lecture for inputs on what to cover on Monday. Good. It's done. See, isn't it fun to do slides with? Yes, I really like that it's really trying, right? So model, there's an airplane. To school, there's like colors. Yeah. Anyway, what is categorization? So categorization is very fuzzy concept, but a good definition that I found in a dedicated paper by Bradley Love is defined as acquiring knowledge structures that enable an agent to make predictive inferences. Right? So think about the alien game. You had to sort of have a knowledge structure of how to recognize specific classes of aliens, dangerous nutritional aliens, so that you could sort of predict how they would act against you or which kind of actions you would need to do in order to deal with them. And it's about clustering experiences in the world according to what we can or should do. So classical examples that people bring up in the developmental literature are what things you can eat, which things are too hot, right? Getting cues from the words so to start behaving in more meaningful ways than a newborn baby. Right? And the question is, since this seems to be a very crucial cognitive process to have across the animal kingdom, perhaps even beyond, right? How do we actually categorize? So the way that the process has been formalized is, I want to put these away. Yes, is according to a sequence of steps that we can criticize in their specific sequence, but they give us useful tools to think through categorization processes. So the first one is input representation. That is, as the word presents us some stimuli, or as the experiment is giving you some stimuli, we need to figure out how to represent those stimuli. In games, as you were operationalizing them last Friday, what was the input representation? How did you turn the cute little aliens into something that the computer could deal with? Yes?
With five, isn't it?
Yes.
Like 0 and 1s.
So you identified, you sort of figure out that there were 5 features, and these 5 features could have a value of 0, 1. It's much more complex when you're a baby in the world, right? But still, we need to figure out how input representation works. And in a sense, a lot of the recent development in deep learning, maybe it's recent for me, for you, it's all the history, but it's how can a system learn how to do input representation without us feeding it too strongly to the system, right? The second is attentional processes. Right? Attentional processes are, how do we figure out which aspects of these representations are important? If you want to be nitty-gritty, right? When I started studying cognitive science, there was a big revolution against boxes and arrows kind of setups, right? And you could say, but actually, as we learn how to represent these features, right, attention is already there. So those two steps are kind of interwoven in real cognitive processes. But for a long time, in all these computational models, what happened is that you have a pre-given space of features, right? And the model has to learn what to pay attention to. What are the attentional processes in the alien game as you were modeling it? And how did we pay different attention to different features?
Some groups add some weights.
Yes, exactly. So weights would be one way of adjusting how much importance these different things are. Third step is intermediate representations. Again, I'm going to have more detailed slides. I just want to give you the general outline of how categorization models have been developed in the field, which is once we have taken the inputs, represented them in a common format, paid specific attention to certain features, we need to sort of store them in our memory. And we can store them in different ways, which we discussed on Friday. For instance, we could store every single exemplar, or we could sort of summarize them. So, for instance, taking all the dangerous aliens that we have met and representing them not as 36 aliens, but as a central, right? As the core of the distribution of these aliens. So for instance, right? If it's the kind of dangerous aliens that we have met. For the people of the Zoom, I'm just making a small cloud of dots in a two-dimensional space. And then I find the centroid and I say, actually, the intermediate representation is simply the centroid of this distribution. And I made the representation on purpose a bit messy, because one could say, well, is it really a good representation of the distribution? Or should we rather identify whether there are clusters within these distributions and say, actually, a better representation is identifying that there are two subclusters, and therefore there should be two centroids, which would be an intermediate representation in between these ideas of exemplars and prototypes, where we're not storing every exemplar, but we're also aware that a category does not need to be a uniform, homogeneous cluster, but there is more structure than that. Does that make sense? Good. Then there's evidential mechanism. Evidential mechanisms, again, I'm going to spend a few words on that, but it's basically given your little monster here, right? And there's at least two categories. Right? How do we calculate the evidence in favor of the monster being part of category 1 and the alien or monster being part of category 2, right? How did we do that? On Thursday? Yes. Exactly, right? So we calculated distances that were weighted by attention, and then based on the distance, we calculated the similarity, right? The more similar to a category, the more evidence in favor of that category. Then there's a decision rule, right? let's say that we have the evidence in favor of the first is something like 6, and the evidence in favor of the other is 5. Right? How do we use those two numbers to figure out how the decision is made? And we've seen, I think we just mentioned briefly that what Rosovsky, who was the guy who did the GCM, did was that, oh, actually, it's a probability which is equal to 6 divided 6 plus 5, right? Which is also called the Luce or Luz or Luque, or I have no idea where that person came from, axiom. But in other models, we've seen that we could just as well model like softmax, right? Which would have a temperature term, which would be a different implementation of this, or we could have a rule that says, as long as there is even a slight advantage, just go 100% of the time there, right? Or any variations on that. And there's surprisingly many terribly boring papers comparing these decision rules and which ones are best, which one best describe human participants across a different contexts. And you can imagine the answer. The answer is, it depends. Okay, and then there's something that's usually kind of underrepresented in these models, but it's learning. So input representation, stimuli are generally represented in terms of features. We've seen aliens that are represented in terms of arms, spots, color, legs, and eyes. Another very common kind of stimuli that is used in this context is faces, where you can represent them in terms of, for instance, nose length, chin to mouth distance, etc., etc. Right? And there's typically two ways of speaking about these representational space for stimuli. Once, when we talk about features, most often the papers are the discrete values that these features can have. In our case, there were 2, but there could be more than 2. While when they talk about geometrical spaces, it tends to be continuous space. But as we've seen, right, there are different traditions in these fields, but really it's the same. You can represent binary features in a Cartesian space. It's not a big deal. When we look at attentional processes, here I'm representing some stimuli, the very same stimuli on a Cartesian plane defined by 2 features or 2 geometrical dimensions. There's a difference in the attention that is paid to one dimension compared to the other in the 2 plots. All right, so if you look, the plot on the top is more round than the plot at the bottom. What's happening in the plot at the bottom is that one dimension gets squeezed, like the vertical dimension gets squeezed, meaning that a change of 1 unit on the y-axis means something in the first, but much less in the second plot. And the horizontal dimension, whatever that is, it gets stretched out, meaning that a change, the distance between 2 stimuli gets expanded in the bottom. Right? So what's happening here is that while here we have on the top 0.5, 0.5 weight on the 2 dimensions, below, I can't remember the exact thing, but we have horizontal something like 0.8 and 0.2 on the vertical dimension. And these reflects the fact that not all features are necessarily relevant given the task at hand. For instance, you quickly figured out that color was not a relevant dimension for evaluating the danger and nutrition of the aliens, but also that not all features are equally relevant given the task at hand. So what might happen is that the arms raise might give you a cue about danger, but it could be a probabilistic cue. It could only work 50% of the time, while eyes on a stalk might matter 100% of the time, or 90% of the time, much more. And also, one of the things that came out from the discussion was that these attentional weights might also be there because we have priors from our real life. So again, if you have raised arms and big teeth, it makes sense that you start with a high attentional weight there because it's the kind of features that are very salient in your other experiences, and that you push your assessment towards danger in that case. Okay, when we move to intermediate representations, right, we have exemplars, means that we remember all exemplars organized by tag category. And that's something that in the literature is often argued for by saying that there are at the very least some things out there in the world where remembering exemplars is very salient. For instance, the example that a few of the people do when they're flirting with evolutionary psychology is, well, if you need to remember your caregivers, right? Your friend, like your grandma and your dad and your mom and your daycare teacher, it makes sense that you remember them as specific exemplars because they will give you different kind of treats and they will provide you different kind of content. And the same is if you're sort of out there scouting for mates, generally it's a good idea to remember the examples. Not, any blonde girl out there should be, potential mate. Though it might describe some data, right? So there's exemplars are also very good because if the distribution of the exemplars within the category is not homogeneous, it's very messy and spread out, then remembering exemplars is actually the best way of solving that problem. You all know the example of games in Wittgenstein, right? That it's very difficult to provide a generalized and even prototypical description of what a game is because games can be so many different things. Right? From chess to hide and seek to whatever, a very complex role play or, hiding yourself in a basement and playing Warhammer and computer games and sports, right? It's really hard to figure out what a good representation of what a game is. Therefore, remembering exemplars, or at least salient exemplars, is a good way of doing that. However, it's memory expensive, right? And in principle, and you would see that in STAN, for instance, if you start having a lot of stimuli, it's also computationally expensive to compare your new stimulus to all the previous stimuli that you've seen, right? As you start accumulating a lifetime of experiences, you have very many exemplars of things. But it's very easy to update. You just add whatever new exemplar you see. When we look at prototypes, we are creating a representative representation of the exemplars by category. For instance, a centroid. And the argument in the literature is this is something that might be very important when, for instance, the costs are very high. When we're talking about danger, when we're talking about potential predators, it might be very good, right, to just overgeneralize, right? You don't need to remember every single predator that you've seen. That would generalize well. You're gonna meet lots of predators in your life. You want to have some cheap representation that might also have some false positives, but it's pretty good at capturing new stimuli in a quick time, right? The idea is that in the at least the central idea of prototypes, there is only one cluster and representation by category. And it's memory cheap, but a bit trickier to update. In this, oh yeah, and then I've already said that, of course, people have then, because researchers tendentially are not stupid, right? They see this table and say, okay, well, what should we do? Can we do a prototype representation with multiple clusters? And then in this picture, there's something that has really puzzled me for a long time because people talk about rule-based models. And what is a rule-based model? So think about games. We're going through these different areas. There were some rules or some patterns that were very difficult to catch. Some aliens that were very difficult to guess. That's because the underlying mechanism that was generating whether the alien was dangerous or not, official or not, had I think it was something like you have to have 2 out of 3 of these features, right? Eyes on stalks, spots, and raised arms, for instance. These kind of pattern is very hard to capture with exemplar and prototypes, right? There is just using the single features without interactions. It's never going to lead you to perfect performance in those cases. But from a good old AI perspective, like the symbolic logic of computers, it's actually pretty obvious. There is a pretty obvious way of representing this, which is 2 out of 3 are danger. And these models are actually very difficult to implement in the kind of models that I do in statistical learning, in hierarchical Gaussian filter, in reinforcement learning, in Bayesian models of cognition. But they are really, really obvious to implement in the early ways of thinking about artificial intelligence. So with languages like Lisp or in R, to actually specify the programming according to logic. And there's now, these are often defined as models in which you can verbalize a rule compared to, oh, you know, this is 70% this and that, right? You can say 2 out of 3. You can say these and that or that should be present. And they have started being represented now in the kind of models that we build in terms of having a pool of possible pre-existing rules, and then using some fancy version of reinforcement learning to update the probability that the different rules are explaining the pattern. Actually, I have no idea how these verbalizable rules would convert into contemporary machine learning classification mechanisms.
Neural net could probably approximate it.
Yeah.
It's just kind of in this framework, it would be a thing that has 1,000 rules that are kind of adjusting a little bit. So that absolutely.
Yeah.
Maybe a neural net with L2 proving whatever it's called categorization.
Yeah, so the idea would be that as you have a rich enough architecture that can automatically represent interactions between the features, then that can approximate rule-based models.
But it would still not be the same process of.
Yeah. Yeah. Yes.
I was thinking that maybe a potential danger would be that a rule-based, we have a better overview of the rules that actually, like, explainability is much better.
Mm-hmm.
Define the rules.
Yes.
And machine learning algorithm could potentially just find some rules and be as humans would need them. No,
Mm-hmm.
or rely on wrong features. Like the classic example of always predicting wolves with high accuracy because there's snow in the background.
Yes. Yeah. Yeah. Big things. So yeah. One of the reasons I've started getting interested in these is that it might be a better description of what happens when we talk about these patterns. Because as soon as I say, oh, maybe it's the raised R's, then we'll actually be able to start testing that as a discrete hypothesis on a trial by trial basis. And so there might be something into the idea that maybe the cognitive system per se in the individual is more a statistical learning, but as soon as you bring people talking about these rules, there's also that level. But I haven't seen a lot of hybrid systems like that. Yeah.
I'm not sure I got the one cluster representation by category, the difference.
Oh yeah, so it was this point that I made before, right? On the whiteboard, so that you have a bunch of exemplars, and the idea is that the prototype model assumes that there is kind of a central way of representing all these exemplars, and therefore it will do the equivalent of finding a centroid, and only the centroid will be remembered. And while the exemplars will allow you to describe this more blobby and bumpy structure. And that's where there's a few models that try to do k-means kind of algorithms, or KNN, right? How many clusters are there? And then can we actually just summarize the clusters within the category? Yes.
Maybe random forest would be kind of rule-based.
Yeah. Yeah, that would actually be a good one. Yeah. And then you also have the combination of several rule-based systems. Yeah. Cool. Yes. Okay, evidential mechanisms. It's the average similarity with representations in that category. That's one way that we have seen. But other ways that people have been discussing this is, well, if we have a prototype kind of setup, we can look at the distance from the centroid. Or actually we could look at the distance between the monster, the alien, and the closest boundary of the category. Right. So if we think of the distribution of exemplars as a bounded figure, then we can identify where it's closest to the new stimulus and calculate the distance from that. It's not computationally very efficient compared to other models, but there are tricks to make it work. There's also something quite crucial that comes up when we talk about evidential mechanisms, which is that as soon as we look at real world data, we see that people's judgment will change according to whether you give them time pressure or not, which seems to point to the idea that people are accumulating evidence over time, even if all the features are presented at the same time. Right? Even if I show you the alien, take it out of the screen, and then I can give you 3 seconds or unlimited time to reach a decision. So there's something in the evidential mechanisms which in empirical data suggest accumulation over time. So for instance, even if we have, if we are accessing perceptually the stimulus, we might be looking at different things over time, right? We have some things that are more salient, which we check first. And then if we have more time, we can check the rest. But even if we sort of took in the vector of features, we can actually start looking at them in a sequential way. You have a point? Yeah. Decision rules. Well, I think I've discussed them before. Don't need to do that anymore. And I just wanted to bring in learning and time, which is really an underexplored area in this literature. We can have that evidence accumulates as we sample or process the stimulus, as I mentioned. We can have that there is exposure to new stimuli and to their association to the category, which we were really, really surprised, for instance, that nobody had ever implemented in the GCM, or at least published on that. Given it didn't take too much work to get it to work. There's the idea that attentional weights are learned, and this has been an area of more active research, but I don't think we have yet good solutions, or generalizable solution, at least, to new tasks. And that's more or less it. And before we take a break, I just wanted to bring in a very cool idea that's been developed by Andy Wills, which is, as decades of mathematical psychology and cognitive modeling have been producing these different suggestions of models, have been implementing different ways of measuring distance, Manhattan distance versus Euclidean distance, Luce axiom versus maximum similarity, softmax with noise, and so on and so forth. It becomes very, very tricky to sort of have an overview of what's going on. And since it might take quite some time to implement your own version of a model from a paper published in the 80s, let alone paper published now, which sometimes since the field of mathematical psychology has had many decades to progress, it has become more and more idiosyncratic. The idea is we need to do better. In that paper called Progress in Modeling Through Distributed Collaboration, a bunch of researchers in categorization are putting out a model of how people should represent stored data sets and models in a way that allow for systematic comparisons between different variants and systematic variability of the different components. And out of that work came a really neat package which does forward implementation of very many of the models in the field. And what do I mean by forward implementation? I mean that you can, given a set of stimuli in a specific format that's very well specified in the documentation, you can get all of the different models to produce their predictions. It means also that you cannot take these models and feed them to participant data. But it is very convenient to start exploring models like Alcove that would take quite a while to implement on your own. Cool. Questions so far? Because, yeah, we can take a break for now. And share the screen. Okay, so I have a question from Sai, if I can get it back somewhere. How do I see the chat here? Okay, so the question here is, one question about intermediate representations. It is often described as static or as though there is an optimal representation for a given data type. But intermediate representations, at least to me, are dynamic in humans. They are dependent on the context, task, and not the actual items themselves. Can GCM account for these dynamic representations? And so the problem with GCM really is that in its original conception and in all the implementations that are out there, it assumes that you've been extensively trained on the task. And that means that at that point, once we can start describing your cognitive system with the GCM, the representations are fixed. Right? The weights have been learned. The GCM is an exemplar model, but we could imagine a centroid-like version of the GCM. And the centroids have already been optimized for the training data. So in that sense, the GCM cannot represent this. In human, we have a much more complex thing. First of all, we might expect that most situations in any child above 1 day are going to be some sort of transfer learning situation where there's already a lot of learning that has gone on, which get used to at least partially shape the performance in a new context. Second, I guess that we could, well, humans learn as an iterative process. They don't start already trained like the GCM. So that also means something important. I was discussing with Andreas during the break how could an update of categories look like over time. And one of the things that was tricky to sort of figure out from the model is as you're being exposed to new exemplars, you see that 3 of the dangerous aliens and in stock. Should that also change your representation of the non-dangerous aliens? And according to the GCM, and especially when we're not learning weights, so given that the weights are already there, what happens is that no, we're only updating the representation of the dangerous aliens. Because in principle, the 2 clouds of dangerous and non-dangerous aliens could be very much overlapping. The exemplar kind of strategy to approach to categorization as that as a strength, right? If there's a lot of overlapping, it's not bothered by that. In more prototype or or category boundary kind of models, which you should be familiar with, what happens is that as we see more and more exemplars, we might need to shift the way we represent the feature space. Think about SVMs. According to the structure of the categories, you might need to change the current that you're using. So my favorite example, because it's just so easy to represent on the whiteboard, is where you have, let's say, on the one on the left and one on the right, 2 clusters of dangerous, 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 and not dangerous, not dangerous, not dangerous. And here, right, you could have simply a line that divides them. But as you meet more and more non-dangerous items, you might actually end up in a situation where you have a donut of non-dangerous items that are surrounding the dangerous cluster. And that's where we would go and use, I can't remember which kernel, but one of the nonlinear kernels for SVMs, right? Which is perfectly able to capture that sort of structure. And in principle, right, we could imagine that our formalization of the categorization system could try different kinds of ways of shaping this space. Part of that is reweighting the weights, but part could be actually doing something more drastic to the topology of the space. And the question is influenced a little by my background, and I feel like anytime I hear of intermediate representation, I think of the discovery of structural form by Kemp and Tenenbaum, which I don't know, sorry. So I cannot comment on that. Is this a satisfactory answer? Yes. Yes. Makes sense. Great. Thanks. Okay. Good. So one of the things that I think I've already brought it up enough, so we don't need to discuss it more, but is like how machine learning classification and categorization are related to each other. And I think that the key aspect is that they're both trying to form categories. And they've been approaching, the two fields have been approaching the same problem from very different angles, right? Where machine learning is whatever makes it, right? Whatever gives us the best out of sample performance. While the categorization literature has been trying to say, well, let's approach the problem from a principled way in terms of what we know about the human cognitive system and in terms of having as separable components as possible so we can separately poke at memory versus decision rule versus evidence accumulation and so on and so forth. As machine learning has evolved to something that, for instance, can learn language from the videos from a camera that was put on the head of Mike Frank's daughter as she was growing up, then these machine learning models can become also models of cognition. And there's been a lot of work that is saying, well, given that they seem to be able to approximate human performance in interesting ways that traditional models are not, like in which ways do we poke them? In which ways do we start running experiments? And so they can both help us sort of reevaluating the classic models of categorization, but we can also do the opposite operation that's saying, if we assume that these actually, even if they weren't meant to be models of human categorization, if they work as model of human categorization, can we explore them in meaningful ways? We can do that, for instance, by changing the kind of stimuli they are learning from. And there's a super amazing project called First 1,000 Days. I don't know if you've heard of that, where they have, now I could be saying something stupid, let's say 16, something in that order of magnitude, families who have agreed to have 8 cameras and 4 microphones for the first 1,000 days of their child's life at home, with the idea that you can actually produce corpora that approximate to a much better extent than what's been possible so far, the actual learning environment of the child. And so seeing where the child is, what the child is engaging, what the parents are doing when they're speaking, what they're pointing to, how close they are to the child. And then we can manipulate which parts of these information is available to the child, to the model that we're training, and see which impact these things can have. The work has been, trying to explore the kind of errors, really poking at the errors that these categorization systems, deep categorization systems are making, to see how do they compare to the errors that humans make, right? And how will we interpret these sort of errors in terms of what they tell about the underlying processes? you can play with the architecture, and I think they're a very good way of pushing some of these research forward, right? They're complementing the line pretty nicely. Are there comments or questions? Good. Or yes. Okay, so we've seen the GCM model last week. Some of you have started implementing it. Many of you, I guess most. Its input representation is traditionally geometric, but we can make it work with discrete binary features. It's been like the distance that the distance between exemplars, I described it as Euclidean distance. But Mina told me very rightly that the original formulation is very agnostic as to the kind of distance. And that indeed, in the code that I provided you, I'm always implementing Manhattan distance. So I went back to my correspondence and I figured out that once Sarah and me were implementing the model, the Manhattan distance actually gave results that were much more meaningful, and it was faster than the squaring and root squaring for some reason. I don't have enough details in those emails to figure out exactly what it was. But now I've corrected in the different slides that we are doing Manhattan distance. The attentional processes are that weights sum up to 1, right? There's weights on each dimension, and the weights sum up to 1. The intermediate representations are exemplars. The evidential mechanisms are similarity as exponentially decaying over distance, and similarity to exemplars by category. The decision rule is the Luce-Choice axiom. And in learning, the traditional GCM separates a training phase, which is taken for granted, where all the exemplars during the training have already been observed, and a test phase. But the implementations that we're showing actually don't have that clear separation. Askel corrected my DAG, which is nice, of how the model could look like, right? Where we can have the choice that is observed together with the features and the category. And we have the choice is determined by a rate, which could have a bias if people are, risk averse and always say danger. But the key rule is similarity, which is determined by distance and scaling, and distance of the current stimulus as represented by the features up there is defined according to what we have in memory. And what we have in memory depends on the previous categories that we've been exposed to. Weights that affect how the space of memory is shaped. Good. So we've seen how to code this last time. And I've corrected an error that was in the code. So if you were copying it from, if you copied it from the slides that were there, even before the break, here there was a sum, but it should actually be a mean. So it's, I also looked at where that come from is because in all of the implementations that we could see in the training phase, the participants were exposed to as many examples of one category as of the other category. And so the sum didn't make a difference. And then I forgot to change things. We went through this code last time. Do you want me to go through this code again? Is that useful? Or we can focus on Stan instead? Huh? Stan? Okay. Yes. Okay, one thing that I just wanted to show was simply as I had to simulate responses for that specific experiment setup, can you see anything on the screen? The idea is that I'm exploring the model and I need to figure out how the different parameters are affecting the performance of the model. Right? That's the first thing we do after we implemented the form. And so here in this simplified setup where we have only, two categories, not the four that you have in your assignment, and only two features, right? The height and the position of the lines on the screen. We have a weights that is a vector of 2 dimensions, and we have the scaling parameter. So what we can do is, here I created 3 vectors for weight. One that's equal weights, where the 2 weights have both 0.5. One that is skewed, which is extremely skewed. One dimension has all the weight, and the other dimension has no weight. And one that is less skewed. One has 10% and the other 90% of the attention. And then as I feed those values to the functions that I defined before, I can generate responses to the setup that we coded last week. And then we can plot it. And then we can see that as we vary the scaling from a very low scaling that is distance is almost linearly related to similarity, to a very high scaling where similarity drops at the first hint of distance. We can see that with equal weight, the performance is exactly a chance when the model is very probabilistic. And as scaling increases, the performance increases. Right. So we know that those features both matter in the real example, right? So we had something like this. And the decision boundary passed exactly in the diagonal, which meant that both of the weights matter. And the 2 parts, vertical and horizontal, are kind of symmetric, so they really matter the same. So what we see is that if we put any sort of scaling, if similarity is indeed as an exponential decay with distance, the model is able to learn the structure of the categories and to give the right answers. When we put extremely skewed weights, right, what we see is that the model is not really able to learn. Why is that? Because the category is determined by both categories. Because the decision rule is really, the decision boundary is really the perfect diagonal. Right. So if you go and only choose using the vertical axis, right, there's members, equal number of members of category 1 and category 2 at all levels of the vertical. Well, actually, there might be a bit of a skew on the top, right? High levels of height will tend to be more associated with category 1, and low level of height tend to be more associated with category 2. But there's enough noise that it's really hard to do much better than the baseline chance. With some scaling, you can get to 0.6, 0.7%, but not to the levels of 0.9 as the model that takes all the evidence into account. As the skew becomes a bit smaller, right, With low scaling, again, we're a chance or below. But with a bit of scaling, we're getting slightly better. Because now we're actually also taking into account a bit of the information from the outer dimension. Does that make sense? Yeah.
Just remind me how you can get less than 50% chance in a two-category test.
Because I ran the relation only once, I guess. And so if you meet, because this is there's no separation between training and test. And I only run one seed, so that's that might happen. The other plot is exactly the same data, but instead I split it by scale, just because it gives complementary information. It says that once you have low scaling, it doesn't really matter your attention. But as scaling increase, you can see that the better the attentional weights match the structure of the category, the more the performance become as you get exposed to enough exemplars. Yes.
So how much scaling is good?
So when I was simulating, I think that basically anything above 3 is indistinguishable from each other. And there is an upper limit to how well you can fit the model if you allow scaling to go high for some reason. So scaling above 2 actually makes your model really hard to fit. So assuming that scaling can go above 2 makes your model really hard to fit. But let me see if I have the 2 is the blue. Yeah, it is still pretty different. The blue from, so the 2 from the 3.
Again, I'm still a bit bamboozled by the lowest scaling that you have there. Because I think when we also ran it with that low scaling, we were also consistently getting the low
Chance.
Yeah.
We have the
6 odds, that's a lot. Så hvis du tog gennemsnit af dem,
well, I'll have to run a few more simulations and see whether that stays constantly below. Yeah. It should eventually get to 5 over time. Okay, so here is how the stand model works. We have a data block, which we're giving the number of trials, the number of features, the group category of the stimuli, the decisions of the participant, the array of 2 dimensions. One is which trial we're in, and the columns are the features, so we can represent all the features that are being describing the different stimuli. In this specific implementation, we have an initial bias for category 1 over 2, which we fix at 0.5, so it's not really making a difference. And then the priors, so that we can compile the model and then feed different priors to the models without having to recompile. So the prior values for the weights, 1. Oh, and the prior, so mean and the standard deviation for the scale. Then we have some transform data. where in the transform data, what we are doing is, first of all, we're creating two separate lists, one for the dangerous and the other for the non-dangerous, let's say, one for category 1, the other for category 2. And which basically, I'm not going to go through all the details, but basically it's creating which indices, like which trials there is an exemplar of category 1 and which trials there is an exemplar of category 2. Then we have as parameters, I think this is crucial, a simplex of length as many as the features there are. What is a simplex? The simplex is a vector which sum is equal to 1. So if we define attention as a simplex of as many values as the features, we get for free that it would always sum up to. We don't need to ensure it out. And then we have a logit C. Why are we considering the scaling as a logit? Well, as I was saying, because so scaling below 0 doesn't make sense. And scaling below 2 made our model really difficult to fit. So here we put two boundaries, a boundary at 0 and a boundary at 2. And once we have a parameter that is bound on both sides, logOts is a very easy way to model it. Right? So we're saying that there is a parameter that's on logOt, that's called logit C, which then in the transform parameters gets transformed into the scaling by saying inverse logit and multiplying it by 2, which means that it can now go not only from 0 to 1, but from 0 to 2. We could put it 3. It's always kind of a bit heartbreaking to have to put these hard boundaries, but sometimes you just get to have the model that works and submit the master thesis. You'll see it next year. We then have two vectors of the probability of picking category 1. And that was a bit of a hack. But the idea is that you could get by chance that you've already seen the exemplar that you are asked to evaluate. And therefore, you will have a probability of 1 or close to 1 to pick the category in which you've already seen the example. If you have a probability of 1, according to the model, and the participant picks the other category, because participants are like that, the model is going to fail. Because there is no way that with a probability of picking 1 of 1, you will pick 0. But the participant did. So here, again, it's a bit of a hacky solution, but we said there is an array of real numbers, which is what we can calculate from the similarities. And then we have a derived probability, which is bound at 0.001 and 0.999. Then for each of the trials, we calculate its distance from the observation to all the exemplars that we have seen. So the exemplars that we have seen are, if we are at trial 3, I equal 3, are the array of length 2, so 3 minus 1, so the 2 previous exemplars. And then loop through that. Look at the distance, Manhattan distance, the absolute distance in each dimension, weighted by the weight. And then the can sum the distance across the different dimensions and multiply it by the scaling factor, change the sign, and exponentiate it. Right, that's just the formula of the exponential decay of similarity with distance. Then, if there's not at least one exemplar in each of the categories, we put R equal 0.5, right? We don't know. We haven't met a non-dangerous alien yet, so the model assumes that we're just going to pick at random. Otherwise, we actually change it yet. Should be mean. Otherwise, we need to calculate the mean of the similarities to category 1 divided the mean of the similarities to category 1 plus the mean to similarity of category 2. And theta is simply the bias because we might be more biased towards danger than not. Yes.
I'm not sure I have the example where there's a probability of one of choosing one category. Would that be if you saw a specific monster in the first trial and the same monster in the second trial? Otherwise, we would have different ones.
It depends. If it is not something that happens all the time, but it happened often enough that we got annoyed and put that hack. But the idea is that let's say that you have these exemplars here, and then you have a bunch of exemplars in the other, but they're quite far. Then actually you might have the two clusters. Then if you have a high scaling and you get an exemplar pretty close or even the very same exemplar here. So the similarity to the close by cluster will be pretty high, and the similarity to the other cluster is going to be 0 because, or almost 0 because it's sort of exponentially decay with distance. And once this distance, the relative distance is big enough, it will approximate to 1. Yeah.
And I guess because of the exponential scaling and this gets close enough to 1 that floating point inaccuracies come into play or whatever.
Exactly. And so every time that we had, since there are clusters in these representations, every time that we had exemplars that were exactly the same as previous exemplars, we would start getting some of these effects.
If you had a softmax weighting, sometimes pick randomly anyway.
Yes, the problem, if I remember correctly, is that scaling and softmax, so the temperature and C would be very highly correlated. Yeah. And so here you can see that it's simply a sanity check. It says if the probability of picking 1 is very close to 1, then convert it to 0.9991. If it's very close to 0, then convert it to 0.001. Otherwise, just copy whatever you got. Then what we had is we had to put priors on weights on logit C. For logit C, it's easy, right? We're working on log odds, so we can again go, if you're me, with a normal, with some values that we decided before, with a simplex, which means that we have buckets, in this case, 2 buckets, in your case, 5 buckets, which have to sum up to 1. The prior for that structure is a Dirichlet or Dirichlet. I guess you've all met Dirichlet in NLP at least, right? And Dirichlet has two parameters. One that express how equally distributed the values are. So the entropy of the distribution, if you want, with maximum entropy being they're all equally distributed. I can't remember what it's called, but it's a measure of variance. The concentration, it's called, which, as we will see in a couple of slides, tells us basically how precise the prior is. We might have a prior that says maximum entropy, meaning that all the weights should be equal. But if it has, I'm going to say variance because I can understand it better. Then I'll check which direction it goes. If you have a low variance, every time you sample from that distribution, you will get basically 0.5. If you have a high variance, every time you sample from that distribution, you might end up getting 0.1 and 0.9, right? Even if on average you will have 0.5. And then, bit of an anticlimax. This is the model. The choice of 0, 1 is determined by a rate R. And that's a Bernoulli, blah, blah, right? Yes. Okay. So the first thing that we do is we run that on the simulated data, and we find that, so here we have each scaling. And here we have one of the weights for equal weights for skewed and for skewed 2, right? Because since it's only 2 weights and they sum up to 1, I only represent 1 to make it easier. With very low scaling, we cannot really reconstruct the true weights of the simulation. As we increase the scaling, again, we get that we can actually reconstruct pretty nicely the actual values of the weight. Again, this is the sort of stuff that we always need to do. So I'm putting these slides, even without too many details, just to remind you that we cannot really do anything with a model until we do this and understand how it works. When we try to recover scaling, we have that, again, the true value of the scaling is in the panel, in the facet. And the colors of the distribution are the value of the scaling parameter is reconstructed when the true weights are equal, when they're skewed, and when they're a bit less skewed. Why? Because I have no idea whether it's going to interfere, right? So we want to check. And it does interfere. We can see that. Of course, this is only one simulation. We should run it several times. But we see that in general, the ability of the model to reconstruct the scaling is pretty decent. Right? It's actually more uncertain than with the weights, but it's decent. Good enough? Yes. 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 Oh yeah. So the idea is think about the normal distribution, right? You have a mean, and then if you have a low sigma, this is the distribution. If you have a high sigma, this is the distribution, right? It should be lower. That's the same with the Dirichlet or Dirichlet, right? That you have a separation of, actually, I have it here. Let me just, I don't know why I'm. So the mean of the two plots is exactly the same. So I'm saying there is maximum entropy. The two weights are on average equal. But in the simulation on the left, I put high concentration, meaning low variance, high precision, low variance. And when I sample from it, I get weights that differ very little from 0.5. On the right, I put a capital concentration
concentration of 1, I decrease the concentration, I increase the variance, decrease the precision, and when I sample, I actually get values of the weights that are all over the place. So the Dirichlet has a parameter that tells us how precise our expectation for that distribution of weight is. And this is how I understand things, right? So there's people who can figure it out in their head. I need to just sample data and see how it works. Yes. For that model, I don't remember, but it's in the course notes. I can check.
But what about the other?
What, sir? Yes. So here I'm just putting it as equal.
So that's not our opinion.
Yes, exactly. I can actually check because I was fixing things just before. So I put a kappa of 1, which is this one.
The right one. Yes.
Exactly. And now we have 3 minutes. So of course we can run a multi-level version of this, right? But the basic idea is that now for scaling, we need a hierarchical scaling parameter. For scaling, it's easy because thanks to the logic trick, we can think of it in terms of a normal distribution. And so we can have a population level parameter, which is a mean and the standard deviation, and then a vector of parameters, which is sample from that. For the weights, we have a population level parameter, which is what we've seen before. So weights as a simplex, right? As a vector of n dimensions that sums up to 1. And then we have concentration, a kappa, exactly equivalent to inverse variance, which tells us how precise the expectation is, how much of an individual variation on the weights from the population we expect. And here, of course, I have no strong expectation that everybody's using the same weights, and that's where I would put a kappa of 1, which is very low precision. And then we have the individual level parameters, which is basically a vector or an array of synthesis. Isn't Latin fun when you have to apply it to English? Which are the individual weights. And we can simulate Dirichlet by putting weights, kappa, and number of agents. And there's a very handy function called R-Dirichlet, sample from Dirichlet, that allows us to do that. And then what we do in span, it's really do the same operation. So the number of trials and number of features is just as before, but we also add the number of subjects because we have several participants going through that. The observed choices, the feature, the observed choices is now a 2-dimensional array where we have as many trials as rows and as many subjects as columns. Transform data is exactly as before. And how was with the transform parameter? The transform parameters. Oh yeah, the difference is that in order to model hyperprior, so the Dirichlet, which is a prior for a Dirichlet, it takes a parameter which is called alpha, which basically multiplies the weights
by the precision. So it works a bit like a beta, meaning that you can have, 1, which is a pretty uncertain even distribution, right? So you have observed, one success and one failure, or two successes and two failures technically, right? And so you're still pretty much flat. Or you could have 100 and 100, which means that you're really sure that it's 50-50%, right? So by taking the weights that were on a scale that sums up to 1, and you multiply by the precision, let's say you might end up with 500, 500. And that tells you that you expect really every sampling from that distribution to be 0.5, 0.5. That's why the alpha is there. And then actually we can go a bit more through that, and I'll get the code corrected next week. If you have things that you would like to see on Monday, beyond wrapping these up, let me know, tell me now, or send me an email, and I can prepare. Otherwise, I have both finishing these and some current frontiers in the field, so adaptive optimization and that sort of things. Cool, but I'll see you tomorrow.